Section 2.3, modeling with linear functions. Linear functions can be used to create models of situations we want to study in real life. For example, here there is a very good example taken from our OER textbook. It says, Emily is a college student who plans to spend summer in Seattle. She has saved $3,500 for her trip and anticipates spending $400 each week on rent, food, and activities. How can she write a linear model to represent her situation? What would be the X-intercept and what can she learn from it? To answer all these questions, we can create a model using linear functions. I will show you next. For example, we can start by labeling with variables X and Y. What is happening in this situation, in this context. For example, I could let X be the number of weeks she's going to spend in Seattle, right? So Emily will stay in Seattle, Okay, now there's nothing particular about the choice of the variables, right? X and Y, but it's what commonly mathematicians choose for input and output values, right? X for input values, Y for output values. You could choose any two letters from the English alphabet, right? And indeed, we will do that in other examples, but mainly X and Y will be used. Now, for Y, I can let Y be the money that Emily has left, after she spends certain number of weeks, right? After Emily stays in Seattle. So after she spends certain number of weeks, X weeks in general, right? In Seattle. Okay, great. So we have used X and Y to label the quantities we are dealing with here, right? Now, know how to see that if I want to see the relationship between X and Y, money left after Emily stays 6 weeks in Seattle, should be equal to 3,500, right? This is what she starts her vacation with. And then as she spends certain number of weeks, this $3,500 will get decreased, right? Will decrease. And how? Linearly, because it says that she plans to spend $400 each week. The rate of change is constant. That is why we can represent this using a linear equation. So we start with 3,500, and in the first week, she spends $400. On the next week, $800, 400 multiplied by 2, and so on, right? But in general, she would spend after X weeks 400 times X, right? That must be subtracted from the 3,500 that she starts with, right? All right, so what you see here is a linear equation, y equal mx plus b. It is what this resembles, right? Slope, y-intercept, right? So this is what mathematicians call a linear model, for this particular situation. So a linear model. And the reason they call it a linear model is because you are using a linear equation. When you graph this equation, that will show a straight line, right? Linear model. All right, great. So now, once you have your linear model, there are a lot of things you can get out of it. For example, they are asking us, right, to figure out what will be the X-intercept of this line. Well, to find the X-intercept, remember, you have to let the other variable, in this case, y, be 0, right? 0 is where the X-intercept appears. So if you let y be 0, and then you solve for X, we will get the X-intercept, right? We get the intercept. So we're gonna let y be 0, y substitute with the 0, and we're gonna solve for x this linear equation. To solve for x, follow any method you know, right? Any method you feel comfortable with. I'm just going to subtract 3,500 from each side of the equation, right? So that I end up with negative 3,500 on the left, negative 400x on the right, and dividing both sides by negative 400, I get my answer, right? For the value of x when y is equal to 0. And then we will interpret that. So this will be this guy, right? But what is this guy? Well, take your calculator, right? Scientific calculator or any calculator that looks like this. I'm using our Desmo scientific calculator here. 8.75 is what I get for this, right? For this quotient, 8.75. Remember, notice I have ignored the sign, they cancel each other. 8.75, 8.75 is the value of x. And in the end, feel free to attach the units, right? X represents numbers of weeks, right? So this will be weeks, 8.75 weeks. So what does this mean? Well, it means that Emily will be able to spend 8.75 weeks after she runs out of money, right? So after 8.75 weeks, Emily will run out of money, right? She will not have more money to spend. So this is how basically we use these linear equations to model these situations, right? And then once you get the linear model, you can answer particular questions such as, well, how long she could stay with this budget, right? 3,500 in Seattle, or other questions that you will see we will be able to answer. Now, after this introduction, let me give you guidelines, right? For you to construct your linear models. We're gonna go over different examples, so use this as guidelines. A good model should allow you to study relationships, right? Observe patterns and make predictions, right? So once you get your model, you should see immediately what's the relationship between the two quantities that are changing over time, right? For example, clearly here, when you look at our model, you see that the relationship is linear, right? Linear. Also, you should observe patterns. For example, if x increases, y decreases here, right? It's a linear negative relationship. Also, you should be able to make predictions. For instance, we were able to predict how long Emily could stay in Seattle, right? Considering this budget, right? Good. Now, these are the general guidelines, but in particular, you should follow these hints for you to come up with a good model. Number one, identify the input and the output values. In our example, the input values were number of weeks Emily will spend, output value, the money left, right? After she spends 6 weeks in Seattle. Number two, convert data to two coordinate pairs. So pair up data, right? Because in a linear relationship, linear function, there are always two variables, right? So you should be able to pair them up accordingly, right? Three, find the slope. The slope very important, right? Remember, for linear functions, the slope is constant. It's just a number, never changes, right? In our case here, the slope was negative 400. And the sign of the slope quickly tells you if the relationship is increasing or decreasing, right? Positive or negative. Number five, use the model to make predictions by evaluating the function at a given x value. Yeah, once you have the modeling, you can let x be some value and find the corresponding value of y, right? Yeah, you can make predictions of that kind, but also you can do it the other way around. For example, if they give you a value of y, you can predict what should be the value of x, right? That corresponds to the value of y by letting y be some number and solving for x. I will explain that with a lot of examples. Number 7, you can answer questions that are posted, right? Yeah. Based on your linear model. Here is another example where we're gonna go into or through this hint, right? For you to see that how you can use linear functions to answer all these questions related to the situation whenever the rate of change is a constant. Here, example one says a town's population has been growing linearly. Very important, this word linearly, right? Because right away you have to think of a linear function for your modeling. In 2004, the population was 6,200. By 2009, the population had grown to 8,100. Assume this trend continues, right? Assume that the population continues growing linearly. Part A, predict the population in 2013. Part B, identify the year in which the population will reach 15,000. Let's solve this problem. Solution. The two changing quantities are the population size and time, right? Population size and time. So for the input, advice hint, always take time. Time always input value, time. Okay, so for the output value, take what is changing over time. Here, what is changing over time is the town's population, right? Town's population will be our output value. Very good. All right, so now label time with the letter T. It's a custom, is something that always mathematicians do. When you are dealing with time, instead of using X, use T. Let T be the number of years after 2004. Okay. Now, the output is going to be town's population. Let P of T, right? Use functional notation. The population at time T, right? P of T be the town's population. Now, as soon as you can, compute the slope, because remember, for these linear functions, the slope is constant, never changes, right? So compute it. They say here that for the year 2004, the population was 6,200. By 2009, the population had grown to 8,100. So subtract these two output values. 8,100 minus 6,200, right? It's difference of populations. Divide that by the difference of the input values. Well, for that, since we are working in years, it's a very common practice to do this. Since all starts at 2004, identify 2004 with T0, 0 years after 2004, right? 2005, identify with T1, 1 year after 2004, 2006, 2 years after 2004, and so on, and so on. 2009 will be clearly 5 years after 2004, right? So when you take the difference, you can do this. The difference between 2009 and 2004, or simply just you take 5 years, right? 2009, 2004. So we're going to do 5 here minus 0, right? It's going to be just 5. So this difference, if you use your calculator, is going to be equal to 1,900. 8,100 minus 6,200. This difference is just 5. Okay. Now, 5 into 1,900, 5 into 1,900 is what? 1,900 divided by 5 is 380, right? 380. So this 380 is the slope, the constant rate of change, and tells you that that is equal to 380 people per year, right? That's the increase on the population per year, constant, 380 people each year, per year. Once you have the slope, then simply write out your linear function this way. P of t, the population at time t, will be equal to 380 multiplied by t, right? 380 each year, in general 380 times t, plus the initial population, which was 6,200, right? Maybe we can write here initial population. As you can see, all these linear models, they come with a fixed amount, initial amount, and then a variable amount, right? Variable amount. So this is it. This is what mathematicians call a linear model. Linear model. Okay. So we got a linear model for this situation. Linear model. Great. Now we're gonna work with this linear model, and we should be able to answer questions, right? For example, part A is asking us to predict the population in the year 2013, right? 2013. So what is that? Well, we have this linear model, right, that tells us what is going to be the population T years after 2004. So we got to figure out what is 2013 with respect to 2004, how many years after 2004. 2004 here is 0, 2005 1, and if you continue this, no hard to see that this difference is just 9, right? 9, very good. So 9 years after 2004 is 2013. So let T be 9, right? 9. So if you let T be 9 and you replace that T equal to 9 into our linear model here, then we should be able to figure out what is going to be the population in 2013 using our linear model here. Very good. So this should be the population in 2013. We have evaluated our linear function at t equal 9. Take your calculator again, guys. Okay, and compute this. Use your scientific calculator or any calculator of your choice, or even this Desmos scientific calculator, right? I strongly recommend you to use. 9,620. 9,620 is what we got, right? 9,000, write it out. 9,620 people in 2013. Conclusion, if the trend continues, right? If the trend continues, our model, our linear model, this predicts a population of 9,620 in 2013, right? Try to remember this, guys, for your special assignments that are coming up, also for the exam that's coming up, right? Very good. So now, to find when the population will reach 15,000, which is part B, right? We're gonna work sort of the other way around. Here in part A, we were given the input, we computed the output value, right? Here we are given the output value, the final population, right? 15,000 they want it to be. We gotta figure out for how many years after 2004 that will happen, right? So we work the other way around, you will see. To find when the population will reach 15,000, we can set our output value, P of t, to be equal to 15,000, okay? And solve for t, So we take our linear function, our linear model, 380t plus 6,200, and make it equal to this guy equal to this guy, 15,000. Very good. And then we solve for t, right? Solve for t. To solve for t, guys, feel free to use any method you feel comfortable with, right? I'm gonna just subtract this guy on both sides, 6,200 to start isolating my variable, right? Let's cancel. 380t equal this difference. This difference, when you get it in the calculator, it should be 8,800, okay? Yes. 8,800. And now, dividing both sides of this by 380, right, to isolate our t completely, we should get the following. T equal, let's check, 8,800 divided by 380. 23.15 approximately, which I can round it to 23.16, right? And rounding it to the nearest 100, right? 23.16 years, right? In the end, feel free to attach your units. T is measured in years, so 23.16 years. Conclusion. Our model predicts the population will reach 15,000 in a little more than 23 years, right? A little bit more. After 2004, or somewhere around the year 2004 plus this 23, right? Which is gonna be equal to 2027, right? 27. At that year, the population will be 15,000 approximately. Right? Good. So you can see, guys, once you have the linear model, you can extract out of this linear model a lot of information, right? You can answer a lot of questions. Okay. Now, guys, what is left is to go over different situations, right? Because there are different strategies I will show you, different forms. So for you to be able to go over your homework problems, your special assignment problems, and the problems on the exam, okay? So let's start with this. Let me ask you to do this easy problem first. And gradually we will go over more challenging examples, right? We talked about population just now, right? How to model the growth of population. So there is a question here that's very, very close to that. So this is number 10. Can you try number 10? It's not that difficult. And as usual, I will give you hints. So try to do this on your own. And if you figure this out, let us know. So it says that in 1,880, the population of a Midwest city was 19,000. By 1920, it had grown to 20,000. If it continues to grow at the same rate, key phrase here, at the same rate, right? When they say continues growing at the same rate, you know that this relationship is linear, right? Because the slope is a constant. What would be the population in the year 1939? Give your answer to the nearest whole number. So round it, right? Whatever you get, you're gonna get probably a decimal number. Round it to the nearest whole number. Yeah, as a hint, I will tell you, get the slope first, right? The growth. And with that slope, construct your linear model, and then using the linear model, you can answer this question, right? You can use this strategy with T, associating these years with 0, 1, 2, 3, or you can directly use this as your T, right? As a year. Yeah, maybe I can give you this hint. Let every year, and let y be population. Or you can use t instead of x, doesn't matter. Slope. It started with this population, ended up with this population, right? So try to compute the variation of the population over the variation of time. Yeah. So 1920. Sorry. Yeah, this is a hint, right? To compute your slope. Kind of directly. Compute the slope, the number of people over this number of years, right? That's the growth, the constant growth. And with that, you can construct your linear function that will model this situation, right? Your linear model. Yeah, so y should be equal to, we're gonna put that guy there, x plus the original, the original population, right? Yeah, let's do it together. It's a little bit tricky. I will show you. Yeah, let's compute the slope together first, okay? So the slope together, 20,000 minus 19,000 all over 1920 minus 1880. Yeah, 25. Yeah, I get 25 here. Yeah, very good. This is the slope, right? Yeah, but I see here that we have to pair up years with yeah, that's the slope. For this year, we have this population. For this other year, we have this other population, right? Yeah, there too. So then one thing you can do here is y minus y1 equal slope x minus x1. And take either this point or this point to be your x1, y1, and that should be enough. This is slope m we already calculated. It's going to be 25. Y minus y1, 19,000 equal 25x minus x1, 1880 here. Solve this for y, you will get your linear function. And then from there, we should be able to answer that question, right? They want to know what is the population at this year. So let's do that. 25x minus this times this. Yeah, it's a little bit tricky. 25 times 1,000. I see some students figure this out. 47,000. 47,000 here. All right. So yeah, great. So that's that. Now adding 19,000 to both sides of the equation. Y equal 25x minus, going to be negative this, right? 47,000 minus 19,000 is just negative, well, this minus this plus to negative 28,000. All right, negative 28,000. This is the linear model, right? Linear model. And with this linear model, then we can let x be 1939, right? Let x be 1939 and substitute it there, right? Y equal 25 times 1939 minus 2800. Ah, I see someone figure this out. Mm-hmm. Yeah, yeah, someone is asking me a question. Yeah, let's see what we get first, okay? Yeah, let's see. 25 here times 1939 minus the 800, 45,600. Mm-hmm. Oh, I see. Yeah, let's check this. Yeah, okay, so let's check. The slope is the change of the population, right? Over the change of time. We got 25, right? Yeah, let's do this computation again. Minus 19,000 over. Yeah, great. Okay. Very good. So this is the growth per year, right? So now with this, we substitute here minus 19,000. Yeah, very good. So this is 7,000. 25 times. Yeah, so let's check. Yeah, 47,000, good. Then adding, here, yeah, adding these two, 19,000. I miss a little zero. Yeah, guys, let it serve as a way to show you that whenever something is not going right, just check. Look, I missed this little zero. This little zero makes a whole difference. But now it's good. Now it's good, right? Just go back to what you're doing and check, and everything will come back to normal. Everything will be okay. Now let's get it. 1939 minus 28, 3 zeros here. Now it's good. 20,475, right? 20,475. 20,475. And that should be the answer, right, guys? Very good. Yeah, you can do it in different ways. I just chose the way that finds the slope first, and then using the point slope form, I computed my linear model. Using my linear model, letting x be 1939, we found the answer to be right. Very good. Very good, Gabriela. Yeah, you got it. You got it. Excellent, excellent. Yeah, okay, so this is one question related to population, right? But there are different uh, contexts, situations, so I will explain different strategies. For example, another strategy will be here. You can choose this to be your first point, right? This is your second point, and just find the equation of the line going through these 2 points. That will be another strategy I will show you, okay? But in this case, I chose to find first the slope and then the equation using the point slope form. But finding the equation going through these 2 points, this and this, also will do the work. Very good, guys. Very good. So next example. Let's choose something basic first, and then we'll move to something more complicated. This one, yeah, this is another strategy. The second one I want you to do is this, the first one, I think. Great, can you try this? This is much easier. Number one, try this, do this, please. It says, if an object is dropped from a tower, then the velocity v in feet per second of the object after t seconds can be obtained by multiplying t by 32 and adding 10, right, to the result. So clearly they're talking about a linear equation, right? Find the function b of t relating the velocity to the number of seconds t. Use this function to find the velocity of the object at time equals 6.3 seconds. Can you figure this out, guys? As a hint, I will tell you straight that, look, the velocity they are saying is obtained by multiplying t by 32, so 32t, right, the variable part, plus the fixed part, the constant part, the part that does never change, 10, right? This is the linear equation. So they are asking you to figure this out when t is equal to 6.3, right? For t equals 6.3. So we do this computation. Yeah, this one is straightforward. Yeah, can you find it? And in the end, attach the units, please. You have your calculator handy, right? Your Desmos scientific calculator, any scientific calculator of your choice. You're gonna need it for the exam that is coming up on Thursday, right? So make sure you practice with your calculator. Yeah, if you finish, let us know, right? Let us know. Yeah, if you finish, let us know. Okay, let's do it together, okay? They gave us a way to construct our linear model, right? They said multiply the time by 32 and add 10, right? This is our linear model. And then they say, right, use your linear model, v of t, to find the velocity of the object at time equals 6.3 seconds. So we substitute 6.3 into our linear model. And as a result, we're gonna get that this should be, let's take our calculator. 32 times 6.3 plus 10, right? That gives me 211.6. 211.6. In the end, feel free to attach the units. Feet per second, right? Per second. That's it. So answer for this question then is just this guy. Yeah, everybody follows? Very good. Very good. Now, let's start developing strategies, right? Strategies so you can easily go over these different situations. So let me show you the first strategy for question number 2. And I will ask you to do some other questions where this strategy might be found. It says a faucet is used to add water to a large bottle that already contains some water after it has been filling for 4 seconds. The gauge on the bottle indicates that it contains 11 ounces of water after it has been filling for 11 seconds. The gauge indicates the bottle contains 25 ounces of water. Let f of x be the amount of water in the bottle x seconds after the faucet was turned on. Write a linear equation. Key phrase here, linear function, right? That models the amount of water in the bottle in terms of x. Linear function means we have to figure out a linear equation related the quantities that are changing, right? Very good. So now a strategy, guys, strategy. Whenever you see data displayed in pairs, probably you see 4 seconds goes with 11 ounces, right, of water. And then you see that 11 seconds goes with 25 ounces of water, right? Pair them up accordingly. So basically, if you write here x and y, for x equal 4 seconds, y is 11 ounces, right? Ounces. For x equal 11 seconds, y is 25 ounces, right? 25 ounces. That's how you pair them up. And this is telling you that 4,11 should be one of the points, and 11,25 should be the other point, right? X2, y2. So basically now we have to find the equation of the line passing through these 2 points, right? That's it. Okay. So quickly you find the slope as we did before, right? Slope, mathematician represent with m. It's just y2 minus y1 over x2 minus x1, right? Y2 is 25, Y1 is 11, X2 is 11, X1 is 4, right? So you compute this slope. Look, 25 minus 11 is 14. This difference is 7, right? 7 into 14, 2, right? 2. This is the slope, 2 ounces per second, right? Per second. Very good. Now, with this slope equal to, and you pick a point, let's get this point, 4,11 to be your x1, y1, right? Doesn't matter really which point you work with, you will get the same answer in the end. And then you apply your point slope form, right? Point slope form. Follow that. And then this tells you the y minus y1, which is this 11, should be equal to the slope 2 times x minus x1, 4, right? And then you just work this out carefully. Y minus 11 equal twice x minus 2 times 4, 8. Add 11 to both sides of the equation. Y equal twice x minus 8 plus 11 is just 3, right? 3 twice x, 2x plus 3. That should be your equation, right? And the equation always in a slope-intercept form. So now you just have to change this y for an f of x for functional notation, and this is your answer, right? This is your answer, guys. Very good. As you can see, it's a nice strategy, pairing up your data, right, accordingly. This is when you see this type of data. All right, very good. So now, using this strategy, right, that I just showed you, pairing up, try to do this one, guys, so we can go over other forms. Let me look for one that requires that. Can you try this one, number 5? Says persons taking 30-hour review course to prepare for a standardized exam, average a score of 620 on that exam. Persons taking 70-hour review course, average this other score. Find a linear function, keyword here, linear function, right? The equation of a line. S of t, which fits this data and which expresses the score as a function of time. Can you do that, guys? Hint, look, 30 hours of preparation leads to 620 points on the exam. 70 hours of preparation leads to a better score. 757, right? So pair up the data and figure out the equation of the line going through those 2 points, right? Yeah, go ahead, guys. Yeah, very good, very good. So I'm gonna write as a hint here, X time Y is score, right? And remember, for preparation of 30 hours, the score is 620. Do this pairing carefully. For a preparation of 70 hours, the score is 757. So clearly your X1, Y1 should be this, right? And your X2, Y2 should be this, right? With these 2 points, compute the slope and then figure out the equation of the line going to those 2 points, right? Yeah, finish this, guys. Yeah, very good, very good. If you have questions, guys, let me know, okay? Yeah, make sure you get used to your calculator, either the Decimal Scientific Calculator or any scientific calculator of your choice, right? So you can use it during the exam. That's coming up on Thursday, right?
Yes, professors, can I have questions?
Sure. Yeah, during the break, I will take questions if they're related to the exam, but this question is related to what the problem that we're doing or to the exam?
to the exam. Just like I want to ask
Yeah,
how many
then
questions
when we are taking how many questions? Yeah, 25 questions I have shown. 25 questions. Yeah, very good. Yeah, more questions during the break. You can ask. Right? Yeah, yeah, it's good. It's good. Yeah, it's a reasonable exam. Aha, Mohina, figure this out. Very good, Mohima. Yeah, you made my day. Excellent, excellent. Yeah, very good. It's not that difficult, guys. You just have to pair up the data accordingly, right? So y2, which is 757 minus y1, which is 620, must be divided by x2 70 minus x1 30, right? 30. So let's do this together. So if you take your Desmos Scientific Calculator, you can choose this fraction form, 757 minus 620, all divided by 70 minus 30. That is 3.425, right? 3.425. Very good. So now with that slope, guys, you're supposed to continue working, right? 3.425. Let's write it out. 3.425. With that slope, you use your point slope form, which is this, right? With that slope, goes here. Y minus y1, what is y1? 620 equal 3.425 times x minus x1, but x1 is just 30. And then you just simplify this so that this is gonna look like in a slope intercept form, right? Distribute your multiplication. X minus here. Aha, more students are have figured out the answer. This, if you do it with a calculator, should give you the following. Let's see. Aha, two more students figure this out. Yeah. Yeah, you can, Gabriela, yes, you can choose either point. The answer will be the same for the formula. That's a good question. Yeah. Gabriela was asking me, right? The choice of this point could be even done with this. Yes, definitely. It will not change the answer. Yeah, very good. Excellent, excellent, right? Yeah, very good. Yeah, when we multiply, yeah, very good, Mohina, very good. Let's show it, right? Because sometimes students want to know also how to use the calculator, right? To type these things. Look, notice how I use parentheses so I don't have to use the multiplication sign. This is 102.75, right? So 102.75, very good. Yep. And then adding 620 to both sides of the equation, 620 to both sides of the equation. This is going to be equal to y equal 3.425 times x. And the sum of these two should be just this minus 102.75 plus 620. That is just 517.25. 517.25. 517.25 should be that, and this should be the linear equation, right? The linear equation. Very good, guys. And this is choice B, I believe. Yeah. Now you may say, Professor, but this looks like this: S of t equal 3.4725 t plus 517.25. Yeah, it's because I have used x and y, right? But when you change x with t as we recommended, right, you can choose t to represent time, and S of t, the score they're using the letter S for score. This is what you should get, right? So this. Very good. Let me explain to you this this type of problem where they are asking you to figure out what is the amount of certain items that must be produced to break even, this phrase, break even. It says a lumber yard has fixed costs of $5,980.60 per day and a variable cost of $0.61 per board foot produced. Lumber sells for $2.31 per board per foot. How many board feet must be produced and sold daily to break even? So what does it mean to break even? To break even means revenue equal to cost, revenue equal cost. This means to break even. So whenever you see that phrase, you just have to say revenue equal cost, right? Revenue controls what you get, the money that you get out of selling your items, your products. And the cost tells you how much money you spend to produce those items, right? Now, if the revenue is equal to cost, there is no profit. They call it break even point, right? This revenue equal to cost. All right, so now clearly the revenue here can be obtained by multiplying this guy 2.31 2.31 times X, if you let X be the number of items produced, right? And the cost, for the cost, you're going to have two components. Look, fixed cost, it says clearly here, fixed cost, plus this variable cost. Let's use a different color here for variable cost. So we start with fixed cost, is this, and then you add to that the variable cost, right? The variable cost. So for the fixed cost, you're considering this 5,980.60, right? 0.60. Just we can write in word fixed cost. And for the variable cost, the one that depends on how many units you produce, for the variable cost, you have this guy, 0.61 multiplied by the number of units you produce, right? The number of items you produce. All right, so now that you have this, now solve for X. Now solve for X. This should give you the answer to this problem. Solve for X. For that, what I'm gonna do is I'm gonna subtract 0.61X in both sides. From both sides of this equation, right? This is 0. But here, this difference will give me the following: 2.31 minus 0.61, right? That is 1.7, right? 1.7 times X, 1.7X. And this is just 5,980.60, right? Now, dividing both sides of this by 1.7, you should get the value of X, right? So take your calculator and using our Desmos scientific calculator, 0.60 divided by 1.7, right? 1.7, and I get 3,518. 3,518 should be the number of units you should sell according to this information to break even. Right? In the end, attach the units, right? Board feet. Very good. You follow, guys, this strategy. It takes. Okay, now let me look for a question that uses that idea. Can you try number 6 now? number 6 now did this. Can you try this? Yeah, but this one requires, I think, yeah, this is the course. Yeah. Yeah, this one requires a trick. So let's do this separately. Maybe this one is better. Per week. Yeah, this one is better. Number 7. Go ahead, try. I'm gonna give you a hint here, guys. Hint, set revenue equal to cost. Why is that? Because they want you to find the break-even point, right? Break-even point. Revenue equal to cost. Sometimes mathematicians represent the revenue function as R of X, the cost function as C of X, right? But they are just the same. So set revenue equal to cost. For the revenue hint, use this guy for the revenue, right? Here. And for the fixed cost, they're saying that this is the fixed part and this is the variable part, right? Yeah, follow that, guys. Yeah, I know some of these problems are a little bit long, but they're all doable. Aha, I see some movement on the chat room. Aha, Anna, very good. Yeah, you made my day. You got it. Very good. Excellent, excellent. Yeah, excellent, excellent. Yeah, very good, guys. Very good. Yeah, and let's do it together, right? So we can cover more forms, more strategies can be shown. So revenue comes from the unit price that you choose to sell your products, right? 3.40 times X revenue. Cost, fixed cost, 4,935 fixed cost plus variable cost, 0.40 times X, right? This is the cost associated to producing one unit. To produce X units is this. And now you just have to solve for X, right? Now solve for X. That's all it takes. To solve for X, what I'm going to do is I'm going to subtract 0.40X in both, from both sides of the equation. Here, 0. This is clearly just 3X, right? Equal 4,935. Dividing both sides by 3, X equal the following. So let's compute it. 4,935 divided by 3 is 1,645. 1,645. And in the end, you can attach handles, right? Handles must be solved to break even. To break even, no profit, right? Revenue equal to cost to break even. Very good. Okay, guys, so there you have the answer, right? This is the second strategy. Whenever they ask you to figure out the amount of items that must be sold to break even. Let's go over the third strategy. And this deals with number 3, I think. Yeah, let me explain this to you. It's a combination of two strategies that we have seen I will explain this. It's a little bit tricky. Number 3. Yeah, I always do this problem separately because it might be a little bit challenging to understand, but I will explain it to you nicely. You'll see. It says, Regrind Inc. regrinds used typewriters platens. The variable cost per platen is $1.60. The total cost to regrind 110 platens is $300. Find the linear cost function to regrind platens. If reground platens sell for $9.50 each, how many must be reground and sold to break even, right? To break even, this important phrase for us, right? Break even. All right, so let's do it together. So first, I know that to break even, cost will be equal to revenue, right? But I need to find now what is the cost function, what is the revenue function, right? So let's start with the cost function. Cost function is equal to what? Fixed cost plus variable cost, right? Very good. Fixed cost plus variable cost. Now, I know about the variable cost. Is this 1.60? But now they say that the total cost associated to regrind 110 platens is $300, right? $300. So from there, I know the total cost is $300 associated to the production of 110 platens, right? To regrind 110 platens. So this is the variable cost associated to this total cost. From there, I can retrieve or find the fixed cost, right? You follow, guys? Fixed cost is this. So look, this is 300 equal fixed cost, which we don't know what it is, but soon we will find out, plus this multiplication, 1.60 times 110, right? 110. 176, right? $176. $176 is the variable cost associated to this. So from there, subtracting $176 from each side of the equation, finally I get the fixed cost. Look, fixed cost is 300 minus 176, right? Is $124. $124. Aha. This is good. Because now that I have this fixed cost, $124, I can finally write out my cost function, right? My cost function. So then my cost function should be fixed cost, $124 plus the variable cost, right? But the variable cost is 1.60 times X, right? In general, for X items produced. So this is my cost function. Now, my revenue function will be easy to get because they say that they're planning to sell each reground platen for $9.50. So that will be 9.50 times X, right? That's the revenue. Now, to break even, remember, we said cost equal to revenue, right? Cost equal to revenue, or revenue equal to cost, the same. All right, so we do that, right? We do that. And then, so we're gonna take this guy, 124 plus 1.60x equal to the revenue function 9.50x, right? Now solve for x, and that will be it. Now solve for x, and that will be it, right? We're gonna solve this for x. I am going to subtract 1.60x from both sides, okay? So 124 here equal this subtraction, 9.50. Yeah, use your calculator, guys. Some computations, they will be difficult to do it using mental mathematics, right? Play safe, 7.9x, right? And now dividing both sides by 7.9, I should get the value of x. 124 divided by 7.9, right? 7.9, that is this guy. But this can be rounded. Look, this can be rounded to 16, right? 15.69 can be rounded to 16. So rounded to 16, approximately 16. Round, right? Platens. Sometimes students ask me, Professor, what is a platen? Well, in the past, right, they used to use write using typewriters, right? The platen is that cylinder, looks like a toner, right? What nowadays we call a toner for printers, but in the past, that was what they used for typewriters. Right? They used to regrind them. All right, so 16 platens is what is needed to break even, right? To break even. You follow, guys? And the equation for the cost, the linear equation that can describe the cost, which mathematicians call the linear model, should be this, right? Linear model. So if we look at the choices, the linear model has to be clearly this guy, right? 1.60 times x plus 124, and then the number of platens to break even 16, right? 16. All right, guys. So a little bit tricky to figure out the fixed cost here, but use this information, right? So I explain, find your fixed cost, and that is what goes here, right? Here. So maybe I should highlight this part. This, that what they got here, this is what we put here as a fixed cost. Mm-hmm. Very good, guys. So this is when it comes to having a strategy to deal with these problems, right? So now probably we should go over some other forms that are not really related to any particular study. They basically use a lot of common sense. For example, number 6. For example, can you try this? I think I gave you an example similar to this, right? Can you try? Yeah, I'm gonna give you a hint there. Hint to break even. Set cost equal to revenue, right? This is the cost function. This is the revenue function, R of x. Set them equal and solve for x. Yeah, practice, guys. Mhm. Yeah, and then we will go over number 12 probably. Mhm. Yeah, and as an additional hint, remember for the cost should be fixed cost plus variable cost, right? And let's write it nicely here. Mhm. Mhm. I think you can identify this with your fixed cost. And for the variable cost, I will go with this piece. Right. And for the revenue should be this part, right? Mhm. So it should go here. Yeah, and try to remember these strategies, guys. When you go over your homework, that should appear there. It should be already there in your account, right? For this part. And when you go over the exam, right? When you take the exam. Mhm. Yeah, set cost equal to revenue and it's solve for X. X represent number of handles molded and sold weekly, right? Okay, let's go over this together so we can go over problem 12 and probably after that we should start reviewing for the exam number 1. Okay, the cost, remember, is given by fixed cost, which is clearly stated here. The fixed cost to run the molding machine is $1,231, right? Plus variable cost comes from the cost associated with each unit that is being molded. So it's going to be 0.30 times X, right? Where X represents the number of units that are molded, right? So the handles. So now the revenue deals with the money that you get out of selling these handles, right? 1.30 for each that you sell times X, right? Number of handles produced. This is the equation. Now we have to solve for X. I am going to subtract 0.30x on both sides of the equation. Here, 1,231 equal, this difference is just 1x. 1 into 1,031 is just 1,231. That is x, right? In the end, guys, feel free to attach the units, right? The units. We're talking about handles here. So we can say 1,231 handles, right? Must be molded. to break even. Right? Very good. And that is here. Very good, guys. So next question, I would like you to take a look at number 12. I will show you number 12 now. Can you try this? Again, these questions either follow common sense or figure them out any way you can figure them out, right? It says you can rent time and computers at the local copy center for $7 setup charge, an additional $4 for every 5 minutes. How much time can you rent for $16? And they're asking you to write out an equation that relates what you have to pay for the rental and according to how many minutes you use the computer system, right? So, and then next to it, the number of minutes that you can get for $16. As a hint, the rent can be broken down as fixed rent plus variable rent, right? Yeah. And the fixed rent, they tell you $7, right? Yeah, the variable rent is the other. The variable rent, yeah, this will be the fixed rent. The variable rent is a little tricky to get it, but I will show you. Yeah, this will give you the fixed rent, right? For the variable rent, try to use this part. They say that for $4 for every 5 minutes, right? They try to use that here for the variable rent. Compute per minute how much you should pay, right? Per minute, and then multiply that by chi, which controls the number of minutes, right? You're renting the computer. Okay, let's work this out together, okay? Here it says that the fixed cost, what you have to pay no matter what, is $7, right? Fixed rent, $7. And then there is an additional cost, $4 for every 5 minutes, $4 for every 5 minutes. So if you divide these two quantities, this will tell you how much you pay per minute, right? Per minute, but that must be multiplied by X, right? Because it's a variable rental cost. So now, once you have that, let's just simplify this. This will be 7 plus 5 into 4. What's that? 5 into 4. Well, let's take the calculator. 4 divided by 5, 0.8, right? 0.8 here. dollars per minute, right? Times X. This should be the linear model, right? That we can use for this particular situation. Linear model. All right, once you have the linear model, it's easy to answer questions, right? Related to this particular context. It says, how much time can you rent for $16? Well, we can let R be $16, right? And figure out to this $16 what X should be, right? That will tell us the number of minutes that we can rent this computer. 7 plus 0.8 times X, right? Let R be 16 and solve for X, right? Yep. Solving for X. 0 here, this is 9, 0.8x, right? Then dividing both sides by 0.8, you should get the following. X equal, let's do it in our calculator, right? 9 divided by 0.8. I get 11.25, right? 11.25. That should be 11.25 in minutes should be the amount of time that we can rent this computer for, right? Now notice instead of X, they have written T, but you know, we can change this for T, right? If you wanna be consistent with this, but again, it doesn't matter really which letters of the English alphabet you use to label your variables, right? T, T, very good, T, this T, T. All right, guys, then the answer should be this guy, right? Very good. To finish with this material, let's just go over, I think there's one more form here that I want you to be aware of. I think it's up here. And then we will start with number 9. Can you try number 9? The others are similar. Number 9 says, normal town high school's pool record for the 100-yard freestyle was 47.8 in 1990. Assume that the record falls at a constant rate. Look, key phrase here, a constant rate means that falls linearly, right? Linearly, of 0.03 seconds per year. What does the model predict for the record in 2010? Will you try that, guys? Hint, R, the record depends on time linearly, right? So try to write R in terms of time here, and then try to go from the year 1990 down to the year 2010, right? Figure out how many years from here to here. That should be your input value, right? Mhm. Mhm. Okay, guys, let's do it together so we can take a look at our review, okay? It says that the record starts at this value, right? 47.8, and it drops linearly, meaning at a constant rate, right? At this constant rate, 0.03 times the number of years that has passed by, right? So how many years from 1990 to 2010? No hard to see if you take the difference. This is just 20 years, right? Okay. So you have to let t be equal to 20 to find out what should be the new record, right? The new record. This is what mathematicians call the linear model. And now we're going to find out what's going to be the record after 20 years. So we just substitute t for 20, right? Very good. Take your calculator, guys, and then do this computation. So R should be equal to 47.8 minus 0.03 times 20, right? Times 20, 47.2, which is the same as 47.20 seconds. At the end, feel free to attach the units, guys. So then this tells us that the answer should be this guy, right? Very good.